We will now talk about three-phase systems. And here you can see three phases described as rotating vectors. So as you can see, it's rotating then counterclockwise, typically. And you can see how then three sine wave is created. And you can mathematically it can be represented as you can see here down. For example, you can do R, Y, and B phase in this case. So this is like what to say the three instantaneous EMF values generated in each phase. In a three-phase system, the source consists of three sinusoidal voltages, as we saw. For a balanced source, that is important, the three sources have equal magnitude and are phase displaced from one another, as we said, 120 electrical degrees. There is also a relationship between mechanical electrical degrees, we will see in the next lectures. Three-phase system is superior economically and advantage, and for an operating view, to a single-phase system. In a balanced three-phase system, the power delivered to the load is constant at all times. You will see that also a little bit later. Whereas in a single-phase system, the power pulsates with time. Here you can see like a very simple 2D sketch of a synchronous generator with a stator and the rotor. And as I said, these are three waves, so we have three separate windings or coils. For example, can be denoted as the RR dashed, YY dashed, BB dashed, which are actually physically placed 120 degrees apart around the rotor. Of course, this is very simplified, but actually it's quite generic and it works well for our purpose here. Of course, one thing we can note is that voltage is generally represented as V, but the EMF voltage or generated from voltage drop in the circuit, it is convenient to use E or capital E for induced EMF voltage. A three-phase system we can start to build from a one-phase system. So we will also see that we can go back and work as a per phase. So very simple, you have a voltage source and a load here's a one-phase load. But we can at the same time just draw it in a three-phase manner, as you can see here. With a three-phase voltage source on the left-hand side, typically shown like this. Here with the EMF. And on the right-hand side, we have the Y-connected load. We could also have a four-wire system where we have actually an impedance in the neutral line. That is also a way to, especially in low voltages, we use that. However, when we have symmetric systems, we have no current actually going in the neutral line, as you can see here. So typically we can study the system, a three-phase system, as a per-phase system, with just applying then the Kirchhoff loop in this circuit, and we can have like for example ER minus the voltage drop VR minus VM, and that's because of course becomes 0. And at the same time, and we can also then exchange the VR with the current and the impedance, and thus we can give an equation very simple for just the current in one phase system, as you can see here. And this is the feature in the book, and it's the same way, but in the book we can use the A, B, and C values, and we can then typically we represent each of the coil of one of the phase of the generator as an EMF and an impedance. So here down here you can see then the voltage A0 between here with the neutral point and A is equal then to the EMF here minus the voltage drop with the current and the impedance set D here. And that equals actually the current coming into the load side times the impedance set R. And so actually a three-phase system becomes quite simple to analyze doing such a process. So remember that if you have symmetric and we have balanced load, So sum of currents should sum up in the neutral point here. We as we know, we have the 120 degrees separated between the voltages. And that gives actually some excellent ideas on how we can use mathematical expressions to analyze this. Here is an overview over how the vectors can be placed. So here we have an alpha, where the alpha represents, in this case, 120 degrees. So we have then alpha, as you can see up here on the this side. This is 120 degrees. And then we can have alpha in square, 240 degrees, and so forth, all working on that. We have also a relationship between phase and line, which is very famous square root of 3. So actually it's a very close relationship here. And also we have an angle difference between phase and line-to-line voltage. But by using simple trigonometric but both function and analysis, we can have a good view on how the voltages are composed together. For example, here we have voltage AB, which represents then the line-to-line voltage. It can actually be composed by the voltage here, AN, and also the voltage up here. So it can be like a sum of this. So actually we can find out that we can represent this line-to-line voltage by square root times VAN times 30 degrees phase displaced. So that's actually a very nice way to represent the voltage vectors. Now look at the relationship between the line current and the phase current in a three-phase delta connected load, like here. Here now I'll use U instead of voltage, but it's the same, just different literature and different way to look at it. So there'll be some slides now where I'm using U instead of V. So when it comes to currents, let's look at how it can be outlined to understand the relationship. So we can have then the current 1-2 phase, and is this one. As we know, we have a voltage U12 equal U, and the length, the rule here is that the vector is pointing toward 1 from 2, U12, and the current is just opposite, so it becomes then, it keeps the 1-2 number, but the current comes opposite, as we can see here. We can then represent that current with the U divided on the impedance set. And the same we can do for current phase 2-3 and 3-1. And they all can be represented from the first phase. Just have the 120 degree displaced of the vector. So each phase has the same magnitude of current, as you can see. Let's now look at how we can develop expression for the line current. So the line current will be then the current go out and into this node. And then this is shown here with the expression. And you can do some changes in the calculation, as you can see here. And then we can have actually a combination between the line current and the phase current with a square root of 3 and a 30 degree displaced. So the angle you find with the tangents to phi, and this is how we find the length or the magnitude of the phasor. So this is very traditional, very standard way to do it, but it's actually a nice way to just actually see it. And the same you can of course do with the line current. Do the same approach, and also with the line current in the third phase. And what we can see from this is that also the magnitude of the line current will be the same, but there will be a relationship then between the line current and the phase current with square root of 3 in this way. So you can see in all these 3 places, here we have square root of 3, here we have square root of 3, and here we have square root of 3. However, you should also recognize that here we have 30 degrees displaced, here we have 150 degrees, and here we have 90 degrees. So this is typically angles that we'll come back to all the time, but just due to these trigonometric relationships. Now let's look at the power in a balanced 3-phase circuits, and I still use the capital U and not the V. Also, the F here means phase. And also we're using then now our ST as to divide each phase with a label. So total power is of course sum of the phase R, phase S, and phase T. And then we introduce the voltage and current, and also the sign for both of them, voltage and current, and also this angle between voltage and current in each phase. So by doing this, we, as is seen so earlier, we can get this long expression. And we know this relationship we also had before. We can use that to implement for each phase. And then we get this expression you can see down here, actually quite long also. We have this relationship. It becomes the cos phi plus cos 2 omega t minus phi. But the difference here is that we got this 120 degree and this plus 120 degree, minus 120 degree. And then we do some simplification still. And then we have this expression here. We have 3 times cos phi. So we just collect this expression from above. And we now can also continue to do some simplification here by putting also cos phi outside here, here. And at the same time we have this expression. Now we can use those relationships as you can see here, and we can actually come down to a very simple equation looking like this. So now we are closing in. That's something you probably have seen before. And we now introduce also the square root of 2 using the RMS values. And we actually, and then this number 2 will then disappear against those. And then we will have these 3 times voltage current and the cosines to phi. However, we typically use line voltage, this here. So we introduce that one, and we can come down to this final equation. Square root of 3 times the U line to line voltage and the phasor current, or the cosine to times the cosine to phi. So this implies that we have constant power. It's not varying with time, and that is also why torque in machines are also kept constant. It will not vary with time due to this here. Now finally look at the total power in the delta and Y connection, or if you have a delta load and a Y connected load. Here we can represent a little bit different, but it's the same. Now we have RST here. Continue with that, and the current here in phase is the I set, the impedance, RS, and the voltage is of course opposite as I said earlier. And here you have the voltage UR set Y, just to represent that it's this Y connection. But we have the RST. So since it's symmetric, you can imagine that this voltage here, UR set Y, is here. Is in the from the start point and up here, R to the Y connection point. So that means actually that it's a 30 degree displacement between the voltage going here and the voltage coming here. So it's a 30 degree displacement. So here we have also an alpha, but this alpha is representing like an arbitrary angle, just so we can have possibility if the reference is also changing here. And if we're using then typically the line-to-line voltage as a reference, that's often we do. And we can have that expression. For the phase voltage, it will be square root of 3, as we know, and also the 30-degree displacement, as I already said. For the impedance, for this delta connection, it will be this. It will be the length of the impedance vector, and also the angle to the impedance vector. For the Y connection, it will be, you can just divide it on 3 to get each phase, the total impedance length, and also you have to have the angle. So let's look how the current will look. So in general form, you will with the current, you will then of course have this expression. With alpha 0, you have then the current then is then lagging the voltage. So definition for the in the Y connected load, you will have this expression. So the thing here is that you have the 30-degree also. So let's put up the expression for total power for each case. Here on the left-hand side, let's start on the delta. This is just using complex power, as we already learned, for each phase over here. Then we put into for the voltage and current, as we showed from the last slide. And the same for each phase, you just put in. Now we have, of course, this cancellation of the angles, 120 minus plus 120. Plus 120 minus 120, and we actually can get to this quite simple expression. And further, we can also put into, we get square root of 3 2 times here, and actually it will come down to this simple expression for the delta power relationship. If you want the active reactive power, you just take the real value S and the imaginary value S in this fashion. For the Y connection, we just do the same. Actually, the difference here now is, of course, the angles and the expression for each of them, the phases. Here you can see we get in the 30 degrees, 150, and we get the 90. But still, it will cancel itself out, and we can get down to the same expression as we had over here. And we get the same simple expression and getting the active and the reactive power from that connection. So in overall, you will get then the same expression even though if you have delta connection or the Y connection. The way you calculate the power will be the same.